Right, welcome back. We're continuing talking about electromagnetic waves. Just now we're talking about the magnetic field created by a current carrying conductor. Remember, we said that electromagnetic radiation is formed when an accelerated charge, okay, an accelerated electric particle moves, okay? Now, light is an example of an electromagnetic radiation, like I said earlier on. And EM radiation, we said, travel through vacuum. They don't need a medium to travel. They travel anyway. They go through space. They don't need a medium to move. And EM waves do not need a medium to travel in. I've explained that. And EM radiation carry energy. Now, this is one very important point now. EM radiation carry energy, okay? Can we find out what this energy is? Yes, that's the answer. The energy of an electromagnetic radiation can be found by the equation E equals HF. What does this equation say? H is a constant, is what we call Planck's constant, and what is the value of it? 6.63 by 10 to minus 34. Okay? And F is the frequency of that EM radiation. The electromagnetic radiation obeys the wave equation. We have seen this earlier on in the same lesson. Now, when we look at the visible spectrum, this is what we get. We have, remember I said light is an example of an EM wave, electromagnetic wave, okay? Now, when we have light, light can be broken down into these colors here: red, orange, yellow, green, blue, indigo, violet, okay? Now, these colors here of light have got different wavelengths or different frequency, if you like. So when we're talking red, we should be talking about a specific wavelength or specific frequency like that. For red, we've got about 670 nanometers. How do we change from nanometers to meters? You should be knowing by now that for nanometers into meters, you multiply by 10 to the power minus 9. Okay, so you have that, the yellow, the orange, the yellow, the green, the blue, the indigo, and the violet, in that way. So you can see as you go down what is happening to the wavelength. The wavelength is getting lesser and lesser. So remember the relationship between wavelength and frequency. As the frequency gets bigger, the wavelength must get lesser. So we're seeing the wavelength getting lesser, going down this range of colors. It means that the frequency is getting bigger and bigger. So the frequency of violet, it's much bigger than that of red light, for example. Okay, the electromagnetic spectrum, all right, here, this is for visible light, the light that we see, white light. Okay, when you break it up, it gives you violet, indigo, blue, green, yellow, orange, red. Okay, I can always remember this one because my grade 7 standard 5 teacher taught me this long time back and say Roy G. Beeve. That is one way of remembering the color of the spectrum of white light. Roy G. Beeve, red, orange, yellow, blue, indigo, okay, red, orange, yellow, green, blue, indigo, violet. Okay, so that's how you remember that. Okay, and then we need to also know that there is invisible spectrum, something that we cannot see, invisible electromagnetic radiation, something with very high frequency this side and something with very low frequency this side. It's also invisible. And what kind of waves are we having here? Those that are very high in frequency in this side of the spectrum of white light, we have got ultraviolet, UV lights. From violet to ultraviolet. From ultraviolet, we move on to X-rays. Okay? From X-rays, then we move on to one with much higher frequency, gamma rays. Okay? Very penetrative kind of electromagnetic radiation here with gamma rays because the frequency is too high. On the lower end of the frequency, which is the side of red, from red you have what we call infrared. Infrared is also invisible. Okay? Much lower frequency, high, longer wavelength. Okay? And then you also have microwaves. Okay, here, microwaves. Then somewhere down there at the end you have what we call radio waves. Very large wavelengths here, lambdas. Okay, and then very low frequencies. All right. Okay, now as we're looking at this electromagnetic radiation, we say it carries energy. That energy we said we can find by making use of the energy equation, E equals HF. Okay? That is the equation. Now, an electromagnetic radiation exhibits a particle nature. It also exhibits a particle nature. The particle constituting an electromagnetic wave is called a photon. Okay, all right, it's called a photon. So we are now going deeper. We are saying this particle that is carrying the energy in an electromagnetic radiation is called a photon. Okay, now for now that is enough. Let's come back in the next section and continue understanding how this photon carries this energy and how we get the amount of energy carried by a photon.